summary of how to do a QRT decomposition with the Givens rotation. So if you have your matrix A and want to do a QRT decomposition with the Givens rotation, how do you behave? How do you deal with that? Remember your formulas for cosine and sine. This is a cosine here, abbreviated C, and this is a sine here, abbreviated S. Cosine is equal to the top over the square root of the top squared plus the element you want to kill squared. The top is, remember, very importantly, the first element of the column vector that you consider. And also remember that this column vector is each time in a lower dimension. Like it's the first column vector. Like with the Hausdorff transformation, you can say that you consider the first column vector inside the submatrix. So if the first time you consider the entire column vector, then the second time you consider the column vector inside this first submatrix, so it will have one less element. Then the column vector in the submatrix, so it will have two less elements, until you reach the 2 by 2 submatrix with your first column vector. That's the first thing to remember about the Givens rotation. The top element is the first element of the column vector inside the submatrix that you consider. The first time the submatrix is the entire matrix, and the kill element is always the element you want to kill. So you can find your cosine and your sine. So cosine is top over square root of top squared plus kill squared, and sine is kill over square root of top squared plus kill squared. This square root of top squared plus kill squared is also simply the hypotenuse. You can simply write the hypotenuse if you want. Yes. So now, how do you place your elements inside your Givens matrix? Remember, you put the first cosine in the ith place. So I is originally the row of the element you want to kill, to eliminate, and J is the column of the element you want to kill. So I mean the first element you want to kill will be the element in the second row and first column of your matrix. Okay, if I write like here, if it is a 3 by 3 matrix, you will want to kill this element here. So second row, first column, and then third row, first column here, and then second column, third row, to get your upper triangle matrix. So I is the row and J the column. So your first cosine, you put it in the ith position, so ith row and ith column. Your second cosine, you put it in the jth row, jth column. Your positive sign, you put it in the jth row, ith column. And your negative sign, you put it in the place of the element you want to kill, so in the ith row, jth column. So you can fill up your matrix, your Givens matrix, and in if in the diagonal you will, if there is no cosine, you will put ones. Okay, if it is a 2 by 2 matrix, of course the cosines and the sines already fill up the entire matrix, so you don't need to put any one in the diagonal, and also you put 0 elsewhere. Again, if it is a 2 by 2 matrix, you have no place to put zeros or 1, so you don't care. If it is a 3 by 3 matrix, yeah, you will always need to put at least one, be it here, here, or here, depending on how you place your cosines. And also you place your sines then somewhere, and the remaining stuff you fill it with zeros. So that's the important point. You place your cosine and your sines, and your negative sign, and your positive sign, not the sign, positive and negative sign. You fill in the remaining diagonal with ones, and you put 0 elsewhere. And that's what is written here. You can read it. Say fill in the diagonal with ones, rest with 0. Then you apply your first Givens rotation, and it will kill one element. That's really the key difference with the Hausdorff transformation. For the Hausdorff transformation, you kill all elements except one in an entire column vector, and for the Givens rotation you only kill one element each step. So yeah, you kill one element, then you apply your second Givens rotation. Again, you calculate your cosine and your sines and the i's, which position is what is I and what is j to build your second Givens rotation matrix, and then you will kill your second element, and then you continue until once you you manage to kill all elements in your first column vector. In this case, as with the Hausdorff transformation, the only remaining element is the first element that will be the norm of the old vector. Again, simply because each time you rotate your vector in such a way that one of its coordinates becomes 0, and so at the end you're left with the same vector but just with other coordinates in such a way that it lies on the coordinate axis of the first element. So again, if you have a if you are in 3 dimensions, x, y, z, you first kill y and then z. So the first time you were rotating the xz plane, and then you will rotate on the once you if y is already 0 and then you kill z, you will rotate on the x coordinate axis. That's what I mean. So again, like with the Hausdorff transformation, it should make sense that the resulting vector has as first element and only non-zero element the norm of the old vector, because it's still the same physical quantity, still the same vector. It was just positioned in another way. And then so for the first time you will need to apply n-1 rotations, because if you have an n by n matrix, your first column vector has n elements, and remember, the first element you don't kill it, but everything else you kill it. So you will do n-1 rotation. Like if you have a 3 by 3 matrix, you will kill y and z, and so you will do n-1, so 3 minus 1 rotation, so 2 rotations. If you have a 2 by 2 matrix, the first column vector, you have x and y, you will kill y, and so you will only do 1 rotation, so 2 minus 1 is 1. So if you have n by n matrix, you will do n-1 rotations for the first column vector. And then the first submatrix that we consider, you will do n-2 times the same thing. Why n-2 times? Because, well, again, you don't kill the first. First there is an element outside the submatrix that you don't consider, which would be here, not inside here. And then again, you don't kill the first element, so you only kill everything else. So if at the beginning you have n elements in this column vector, and that you don't consider one element because it is outside of the submatrix, and then not another one because it is the first element, the element we don't want to eliminate, but we kill everything else, we will do it n-2 times. And then for the submatrix, you will do it n-3 times until you reach your 2 by 2 submatrix, where you will do it one last time. Okay, remember, you consider the first submatrix and the submatrix, then the submatrix until you reach this 2 by 2 submatrix, where you will do it once. Because if I can write here, you will have your remaining elements, and you want to kill this one guy here because it is below the diagonal. Everything else is above, and so we don't care. Because remember, at the end, you want a not-per triangle matrix, so that will be the form of your matrix. Yes, it will be like that if you can read it. I mean, see it. So here everything's 0. Above, we don't care, and remember that the first element above the diagonal for each column vector will at the end be the norm of the old column vector inside the submatrix. So again, if you consider the entire matrix, your first element will be, as said here, the norm of the old vector. Once you consider the first submatrix, the first element above the diagonal will be the norm of the old column vector inside the submatrix. Because remember, you don't consider the element outside, which would be like here. You don't consider it because it is outside, and then you continue like that until you reach your 2 by 2 submatrix. So each time the element above the diagonal, the first element will be the norm of the old vector inside the submatrix. And so, so the first time you need n-1 rotation, then n-2 rotations, until you reach your 2 by 2 submatrix. So we do it one last time. Okay, the 2 here is for the 3 by the 3 by 3 submatrix. Okay, the column vector where you only have 3 elements, where you kill y and z. The 3 here is for the column vector where you have 4 elements, you kill 3 of them, and here we would have 4 because you have a column vector with 5 elements. I hope you see what I mean. And then at the end 0, because I said the last column vector we don't really we don't consider it to get our upper triangle matrix. So at the end you have n-1 plus n-2 until plus 3 plus 2 plus 1 plus 0. So at the end you will remember the sum from 1 to n is n times n-1 over 2, but here n is n-1, not n. So we replace n with n-1, and you get n-1 times n-1 plus 1 over 2. So this one here cancel, and you're left with n-1 times n over 2. So that's the number of times we will do. We will need to rotate. Like if you have 3, n is 3, so n-1 is 2, 3 minus 1 is 2, okay? Times n times 3, so 6 over 2, 3. So we will do it 3 times. That is the case for a 3 by 3 matrix. Like we will kill this element here, and this element here. Everything else we don't care. And again, the first element above the diagonal then will be the norm of the old column vector inside the submatrix. And then again, so just first compare that to the Householder matrix. So it is a lot slower to use the Gibbons rotation than with the Householder matrix, because with the Householder you kill one entire column per transformation, and here you only kill one element. So for the Householder you do it n-1 times. Here you do it n-1 times n over 2 times, which is a lot more. Okay, so for small dimension it can still go, but the higher you go, the more difficult it is. Like for a 3 by 3 matrix, you do it 2 times with the Householder, but 3 times because there are 3 elements to kill with the Gibbons rotation. For a 4 by 4 matrix, you do it 3 times with the Householder, and 1, 2, 3, 6 times with the Gibbons rotation. So it's already a lot more complicated. For a 5 by 5 matrix, you do it like 4 times with the Householder, and how is it? It is 10 times with the Gibbons rotation. So it's already a lot more complicated. So just imagine if n is really large, like 100 or 1,000,000 or whatever. It is really complicated. So in an exam, if you need to do a QWERTY composition, I advise you to use the Householder transformation because it is much quicker. Yes. However, I have heard that the Gibbons rotation is more precise than the Householder transformation, if I'm not wrong. But for an exam, you don't really care about that. That's more if you do it with the computer. I've heard that that the Gibbons rotation gives more precise results than the Householder transformation. That's yes. But manually, if you do it by hand, use the Householder transformation because their precision is not the problem. Yeah, so now remember that A is equal to QR, where Q is orthogonal, so its inverse is its transpose. So if you know that Q transpose A is equal to R, and we also know that if you apply all our Gibbons rotations to A, we get also our upper triangle matrix R. That means that Q transpose is equal to the product of all those Gibbons rotations, and so that means that Q is equal to the transpose of the product of all those Gibbons rotation. Okay, so here J G sub n-1 times n over 2, okay, because we do it in total n-1 times n over 2 times the rotations, times this n-2 times n-1 over 2 until we reach this sub 2 sub 1. All the product of all those rotations transposed give us our Q. And so you can find Q. And so again you can apply the A times B transpose is B transpose times A transpose, and so you invert everything in the process for the product. Yes, and so remember the geometric meaning of what we did is simple. All we are doing is rotating. We are rotating vectors in such a way that the resulting vectors lies at the end only on one coordinate axis, okay? So again, if we are in 3 dimensions, like here, we have x or z elements. First, we rotate in the xz plane, okay, that is z, that is x, that is y. We rotate in the xz plane so that the y component is 0, so here, and then we rotate again that will lie on the x-axis, so the x element is non-zero, but the y and the z element are both 0. So this is really we are only have a rotation matrix. Remember what the rotation matrix does? It simply rotates vectors. That's really all we are doing. We are rotating in such a way that at the end you only have one non-zero element in the vector. That means that it lies on the coordinate axis. It's really as simple as that. We are doing nothing else. And for the given rotation, we are rotating clockwise. Okay, because if you multiply the vector 1 0 and 0 1 with this given rotation in 2 dimensions, you like if it is like that, after the rotation it will be like that. It will turn clockwise. If you put the negative sign in the top right corner instead of the bottom left corner, okay, here the negative sign is in this place in the bottom left, but here if the negative sign is in the top right, and so that you have a positive sign in the bottom left, you will rotate counterclockwise. You can also do it like that if you want. It's the same result at the end. But generally we do it clockwise. Why, I don't know, but I learned that way. But it is totally correct to do it in the other way. I mean, I don't see why it wouldn't be possible. It's the same thing. After all, we are still only rotating. So if you do it like that, and you apply it to your identity matrix, so the vector 1 0 and 0 1, you get something like that. So rotated counterclockwise. It's the same thing. So all we are doing is rotating. That's really, I really want to focus on that. We are only rotating, and also the cosine and sine here, the formulas don't come out of nothing. You learn at the very beginning of your school career that cosine is equal to the adjacent over the hypotenuse, and that sine is equal to the opposite over the hypotenuse. And that's really what we are doing. Our top element here is the adjacent, and our kill element is the opposite. Like if you are again in 3 dimensions, you can only visualize in 2 and 3 dimensions. That's why I use 3 dimensions and not more, because you cannot visualize in more dimensions. In 3 dimensions or adjacent, it is a top element, and the top element in 3 dimensions is the x-axis, and so the adjacent is simply the x-axis, and the opposite will be the first time the y-axis, and the second time, once y is 0, the z-axis. So simply the first time it's like that, so this is the y and the x component, and the second time it will be like that. Okay, so here is y basically, here is x here, and the things that point out will be our z, and that will be the opposite for the second rotation in 3 dimensions. And also the hypotenuse, it's simply the square root of both, because both form a triangle. Okay, the x and the y axis, they form a triangle, so we can apply Pythagoras. That's really what we are doing. This hypotenuse is this comes from this triangle here, and so in more dimensions it's really the same thing. So really I want to focus on that. It's really we are doing simple geometry. I really hope it is clear. Yeah, so that's it. I hope you understand it. I hope I forgot nothing. So yes, thanks for watching.